Well, as I've said before, most differential equations we don't really know how to solve. They have to be in a special form in order for us to be able to solve them. And the type we're going to solve next is related to what's called the Cauchy-Euler equation. It's pretty specific. Let's first define a Cauchy-Euler equation. The linear differential equation, an x to the n nth derivative of y, plus an minus 1 x to the n minus 1 y to the n minus 1, n minus first derivative of y, all the way down to a1 x y prime plus a0 y equals some function of x. That function in that form is called the Cauchy-Euler equation. Now, all of those a coefficients, the a sub i's, they're all just constants. Well, we have solved equations similar to this where there was no x to the nth power, x to the n minus 1 power, where the x's didn't exist, where we just had constant coefficients. Now, it's important to note that in the Cauchy-Euler equation, every term, the power of the x has to match the derivative of the y. That's the Cauchy-Euler equation. And the theorem that we're going to write down in just a second shows a way for second order differential equations. So the n is going to be a 2. Shows us how to convert the Cauchy-Euler equation into a second order dE that has constant coefficients. In other words, we'll get rid of the x term in front of the y derivatives. Okay, so the Cauchy-Euler theorem says if we have a x squared d squared y dx squared, the second derivative, that's like y, it's like y double prime right here, plus bx dy dx, so bx y prime plus cy equals f of x. And I need to make sure we say for x greater than, strictly greater than 0. Then a times d squared y dt squared plus b minus a dy dt plus cy is equal to not f of x, but f of e to the t. It's a very simple sounding theorem. We haven't derived why that's true, although I might do that in the next video. But notice this y here, this y prime and y double prime, is exactly the same y here, y prime here, and y double prime here. What we're saying is the solution to this is, let me say it this way, the solution to this is the same as the solution to this. And this no longer has an x squared or an x term at all. We know exactly how to solve these second order ODEs, linear ordinary differential equations with constant coefficients. And you might figure out that when we do show how to get from here to here, an easy place to do a comparison is after the equal sign. The f of x is here, f of e to the t is here. We're probably going to start off with a substitution that says, well, let x equal e to the t and see what happens. That'll be in a future video. Okay, let's look at an example that's going to be pretty easy because we're making it a homogeneous equation. Our f of x, or g of x, depending on which one you're looking at, is 0. And notice this is a Cauchy-Euler equation, x squared, y double prime. X to the 1, y prime, and a constant times y. So the first thing I'll do is just make a note that the coefficients are, I'll say note, A is equal to 1, B is equal to -1, and C is equal to -15. I'm going to have to write kind of small here. I don't have too much to write, but all right. So from this, I'm going to say that the Cauchy-Euler theorem gives us the following equation. The x squared goes away. Well, it's nice that a is a 1. We just end up with d squared y dt squared. So I didn't want to write y double prime here because we think of y double prime as being second derivative of y with respect to x. So this is the second derivative of y with respect to t minus 2 dy dt minus 15y equals 0. So when we solve that, we'll almost have the solution to this. You'll see why almost in just in a couple of minutes. Okay, so where did the this -2 come from? Well, it came from the formula. B minus A is the -2. B minus A gives you -2. And then this coefficient was just a 1. And this coefficient was, that should be -15 there, is -15 here. So this is just a homogeneous case of the differential equations we've been solving for the last several weeks. So I'm going to go ahead and, this would be m squared minus 2m minus 15y equals 0. That means m plus m minus equals 0. It's going to be a 5 and a 3, and the 5 is going to be negative. So our two roots are -3 and 5. And hopefully you remember what that means when we get the two distinct roots. It means we're going to have C1e to the -3t, a C2e to the positive 5t. So I will write, I'm going to go ahead and out of habit write our complementary or our homogeneous solution, which is the true solution since it's a homogeneous equation here. Y sub h is C1e to the -3t plus C2e to the 5t. I'll go ahead and put a box around that, but that is not our final answer. We're going to have to do one little thing that I already mentioned, although I didn't write it down. Maybe I should have derived this first. Going from here to here, maybe I'll make a note. We used the substitution x equals e to the t. So I need this not to be t's here, but I need to have x's on the right-hand side. So what does that mean if x is e to the t? That means t is equal to what? If we took the ln of both sides, I think that would give us t on the right. T is equal to ln x. That's the substitution we used. That's how we get back to the final solution, where the t's on the right-hand side go away and we get x's. So we will have y h is equal to C1 e to the -3, but instead of t, I'm going to write ln x, plus C2e to the positive 5 ln x. Okay, well, let's simplify that. That's not a nice form to leave it in when you have an e raised to something that has natural log in it. You kind of have some inverse properties going on there. That means that C1, well, let me write it like this first. Remember that this -3 can be put up here as an exponent to the x. So e to the ln x to the -3 plus C2e ln of x to the fifth. And so in pre-calculus, I usually remind them that e to the ln, whatever you want to call it, is just equal to whatever you want to call it. E to the ln, this is equal to the this. So final answer, C1, x to the negative 3, that simplifies to x to the negative 3, plus C2 x to the fifth power. And that is the solution to this problem. In the next video, we'll show why this works, why this substitution works, and can take you from this equation to an equation that looks like this, which is much easier to solve.